Alright, so we're going to talk about the electric field and the electric potential today. We're also moving towards talking about circuits, and so that's going to be important in the coming chapters. We've talked a lot about like theoretical electric fields and things like that, but the really interesting part of electricity is when we get to learn, okay, well, how does this actually work in circuits? And we're working up to that today. And so what does the electric field look like in the parallel plate capacitor right here? What do we already know about the electric field in a parallel plate capacitor? It's uniform, yeah, and it flows from what to what? Positive to negative, there we go. Right, and so we've got the electric field is uniform, and it is flowing from positive to negative. And my lines are curvy, but the field is not. It runs directly perpendicular to those plates. What then in your mind could these dashed lines be? We've accounted for the horizontal lines, but what are these kind of parallel to the plate dashed lines? What could those be within this? Good guess. The electrical field created by the plates, though, we know runs directly between the plates. So that's the solid lines. I'm asking, what are the dashed lines? We talked about them. You might know them over here better. We talked about them in terms of point charges and these dashed lines. Yeah, the equipotential lines, right? Same thing in the parallel plate capacitor. And so we've got the electric field lines, right? And then the dashed lines would be our equipotentials. And equipotentials don't tell us about the electric field. What do they tell us about, though? Yeah, kind of. The strength of the attraction. Electric fields... electric fields we've measured in a different thing. The equipotentials, though, like, and maybe if I move from point A to point B in a capacitor, right? What do I call the difference between these points? It's not the difference in the electric field. That's uniform. Right? If I go from A to B, what does change? Not the electric field, but yeah, the electric potential, right? And so the take home from this, what I've now made a very messy drawing, is that the electric potential lines, right? I don't want all of that gone. The electric potential lines run perpendicular to the electric field lines. And so that's something noteworthy here, right? Electric field, electric potential runs perpendicular to it. Same thing here. If I have a positive charge, I've got the electric field going outwards, right? The electric potential is always perpendicular to the field, right? And so when you're looking at these diagrams, we usually use dashed lines for the electric potential, right? And to show us equipotential lines, whether that's equipotential lines in a capacitor or equipotential lines around a charge. Dipole I'm not going to get into too much with you guys because that's a really complicated one, but it works the same way, right? The solid lines are my field. They go from positive to negative. And then I've got my equipotentials, which always run perpendicular. Right, which also explains kind of why we get these funny shaped equipotentials around them. Alright. With this new knowledge about electric fields and electric potentials, right, they always run perpendicular to each other. We've already made an assumption about the electric field within a conductor. What was that assumption? that within a conductor what? It's distributed along the surface of the conductor, yes. But what about inside of that conductor? Right, like the airplane being struck by lightning. Yeah, there's no electric field on the inside of a conductor. Right, we had to make that assumption. I'm adding one assumption to conductors, which is that the electric potential in a conductor is the same. And so it's not zero, but it doesn't change as you move across the conductor. And so the delta V in the conductor, the change in the electric potential, is zero. Whatever the electric potential is when it hits the surface of that conductor, it's the same in the middle. It does not change, right? This also, I like this diagram because it shows you that very close to a conductor, right, there's a strong electric field, and then as you move away from it, the strength of that field decreases. And kind of the same trend is true of the electric potential, right? It is very high when you are close to the conductor or the charge or whatever that is, and as you move away, that electric potential decreases. Okay. And so today, our whole topic, because we're moving towards circuits, is about capacitors. And we've talked about capacitors in this shape, right? There's a positive plate and a negative plate. What do we know about the positive and negative charges of the plates? Is there one where I have more positives than I do negatives? No. So we can say that they're always going to be equal and opposite charges in the plates. Good. What are capacitor plates made of? Metal, which we can generically classify as yeah, they're made of conductors. What does the electric field look like within the plates? Straight across from what to what? Nice job mastering that one then. From the positive to the negative, right, is my electric field. Is there an electric potential within the space between them? Electric potential is V. Yes, there is. If the plates themselves are conductors, is there a change in electric potential within here? No, because they're conductors, right? And we just made that assumption. There is no delta V within that conductor. But in the space between them, yes, that works. There is. Okay. Can parallel plate capacitors do work on a charge? Can they change its overall energy? Either potential or kinetic. Like if I plop a charge down in here? Yeah, it can, right? This positive charge is going to want to go which way? Right, yeah, away from the positive to the negative. That gives it both a change in kinetic energy as well as potential energy. And if there is a change in energy, right, delta K or delta U electric, work is done. Good job. That's all review. If the electric field lines run this way, right, we said perpendicular to the plates, which way would the lines run for the electric potential? Again, V. Or where are my equipotential lines? Yeah, straight up and down, and I see you guys doing that, right? And so all of this area has the same electric potential. We can call that V sub 1. All of this area has the same electric potential. We can call that V sub 2. All of this area has the same electric potential. We could call that V sub 3. What assumption did we make the other day about the electric potential of the negative plate? Just for arbitrary kind of calculation purposes. Yeah, we call this one 0, right? And then we build up as we go, because that made it easy. All right, we already know these formulas about capacitors, about the electric potential, about the potential energy, and about the electric field. We know the visualizations for all of those as well. Real capacitors look like this, right? We've had our nice little diagram. Real capacitors we kind of roll up and put into a little bundle that we can use in electric circuits. And so what this actually looks like on the inside, if I were to cut it in half here and look down, I've got an inside metal plate, an outside metal plate. One of these touches the outside metal plate, one of those touches the inside metal plate, and we get a buildup of charges, right? And then this would be like the space between them. And so, yeah, when I kind of take a little sectional view, I could see how that could look like a parallel plate capacitor, right? Know that what we've drawn so far is not what they really are. They actually look like this, and we'll deal with capacitors when we build circuits. But they work pretty much the same way. We use capacitors in circuits to store charges and to store a buildup of charges. What do we already know, even from outside of physics class, that stores a charge in circuits? What do you plug into every electronic device ever? A power supply, or if you don't have like a cord, what does it have, like your phone or a camera or something? How does it get energy? Battery. Yeah. And a battery, much like a capacitor, stores a positive and negative charge. Same kind of thing. Mm-hmm. Oh, really? We'll do it today. We should have time. That's okay. We should have time. And so a battery stores charges, right? It has a buildup of positives and negatives, and it does that chemically. Capacitors kind of do the same thing in a circuit. The advantage of capacitors over batteries is that capacitors can unload their charge very quickly. And so we get this buildup of charge, and they can unload it really, really fast. For batteries, both advantageous and disadvantageous, is that they take a long time to unload their charge, right? And that's why we use them in a lot of stuff, that they last for a long, long time. They can hold that potential difference. Capacitors can't. Not really. And so capacitors are used like for the flash bulb of a camera, something that has a very quick release of energy. We use capacitors, not batteries. Right? For that reason, capacitors are also very dangerous because they unload quickly. You know, if you touch two ends of a battery, nothing's going to happen. If you touch two ends of a capacitor, it's going to unload that charge really quickly into you. Yeah, right. Which is why things like TVs and camera bulbs have warnings on them, like, do not open this up unless you're a professional. Okay, so the ability of a capacitor to store charge and kind of hold on to it and hold on to either lots or a little bit of charge is called its capacitance. Right? That's kind of like how much oomph it has at holding charge, how good it is. Capacitance does have a formula and it does have a unit. Capacitance is equal to charge of the plates, right? Absolute value charge of the plates, because we know they're equal and opposite, over the voltage difference, or the electric potential difference. You don't like it, Lisa? Right. The units of these, a lot of them are compound. So what is the unit of capacitance? Yeah, it's coulombs over volts, right? And that was actually my next question. The unit of capacitance is coulombs, charge, over volts. But scientists are lazy, and we don't call it coulomb volts. We call it a farad. I know. I'm sorry. You just told me this was a problem, and I made another one for you. And so when we talk about farads, it is coulomb volts, coulombs over volts. Another compound unit, right? And if you want to talk about compound units, a farad is one, a joule is one, a newton is one, right? And we're dealing with all of those. An electron volt is one. And yeah, it's capital F. Yeah. A volt is a compound unit, right? Everything we're dealing with is compound units. And if you want to deconstruct them when you're working and make sure you're ending up with the right stuff, you absolutely can, but I'm going to tell you it's going to get really messy really fast. Extremely messy really fast. Because every unit that we're using right now is a compound unit. But if you want to, I can dance that dance. That's okay. A large capacitance, right, a large farad number indicates to me that I can hold more charge per potential. And so a high capacitance indicates to me that I can hold lots and lots and lots and lots of charge for very little difference. Right? And lots and lots and lots of charge means lots and lots of potential energy. Generally speaking, normal capacitors that we use microfarads or nanofarads, right? And just like our charges, because we're dealing with small amounts, typically. Doing okay? All right. And so when we see a capacitor in a circuit, and when we do circuits, we'll do more of this, but we see a capacitor, and it looks just like parallel plates, even though that's not what the real thing looks like, right? Just like a real light bulb doesn't look like this. This is the symbol that we use for a capacitor, because we use parallel plates to understand them. Capacitors store charge. That's all they're meant to do. And so when I run this circuit, what's going to happen is electricity is going to flow out up to the light bulb. When electricity hits light bulbs, what do? They light up, yeah. That charge continues to flow, and then once it hits the capacitor, it's going to start storing up positive and negative charge on the plates, right? And it's going to continue to do that. Some of this electricity will make it back, right, in the first round. In the second round, the bulb is still lit up, continues to charge the plate, builds up, charging the plate, a little bit of electricity makes it back to the battery. Until I have completely charged my capacitor to its capacitance, it's full. In which case, once this is full, no electricity is going back to the battery. If no electricity is going back to the battery, what happens to the light when the capacitor is fully charged? It turns off. Absolutely. It turns off. If then, with a fully charged capacitor, my light is off, my battery is dead, if I circumvent this and just connect these two wires, right, take out the battery and replace it with a connected wire, this capacitor will instantly unload its charge. It will probably blow the bulb, and the charge will then be equally distributed throughout that circuit. So when my capacitor is fully charged, right, my battery is dead. It has unloaded all of its charge. My bulb is not lit anymore because there's not electricity flowing through it. And so if I take this battery out of the circuit and replace it with just a wire, right, that connects to all of the other wires in the circuit, the capacitor will completely unload its charge almost instantaneously. Right? It was storing it, storing it, storing it. We've given that electricity a route through which to flow, a conductor. It will unload its charge instantly. This bulb will flash, it will probably blow, and then the whole circuit will be equalized. There will be no more charge on that capacitor. The filament will be blown. Right? And so in that way, capacitors act a lot like batteries, but just very, very fast. Right? They store a charge, lots of potential energy, and they unload it instantly. Batteries, same thing. They store a charge, but they unload it a lot slower, and at a reasonable rate for something that uses electricity. Right? We're going to be building circuits in a few weeks, and this might make a lot more sense. All right, so capacitance, we've got these two formulas. Capacitance is measured in charge per change in electric potential. If we are specifically talking about a parallel plate capacitor, right, this becomes the formula. And that's a lot like the other parallel plate capacitor formulas that we've seen before. It depends on the area of the plates, right, which depends on the shape of the plates, whether they're circle or square, and then the distance they are apart. All right. Because we use capacitors to store charge, a lot of times we're interested in storing a lot of charge with a small capacitor. And so we can build greater and greater and bigger capacitors to store lots of charge. Or we can use what's called a dielectric. For size reasons, a dielectric is a lot more practical than just making giant capacitors, right? Because if I'm trying to fit something in the space of a camera that holds a lot of charge for the flash, then if I build a giant capacitor, I'm looking at a giant camera to hold that capacitor. If I can increase the capacitance with what we call a dielectric, then that keeps the size small. And that's really advantageous to us. We know we like convenience as humans in electric circuits. And so a dielectric is any kind of insulator that's put between a capacitor. And so when we think about our parallel plate capacitor, right, we've got the plates. We take some kind of insulator and literally just stick it right in the middle. That's it. Right? That's all a dielectric is. It's a fancy name for an insulator between a capacitor. The typical ones that we use are air. Yes, air is an insulator. Teflon and Pyrex are used a lot. And water. Right? And so water would be like an example in your cells. If we're looking at the buildup of charge between a cell and a cell wall, there's water in between. That would count as the dielectric. That helps it build up a greater charge per area. When we put an insulator in between two parallel plates, two really important things happen. One is that the capacitance is increased, and that's kind of the end game of it. Right? We want to increase the amount of charge that we can hold per area. The other interesting thing is that the electric field, the net electric field, is decreased, and I'll explain that here in a second. Depending on the material that we use, whether it's air, Teflon, Pyrex, or water, each dielectric has what we call a dielectric constant, which is like its ability to insulate. And so some things are able to add capacitance greater than other things. And so we call this kappa, which is a Greek letter. Kappa is the dielectric constant. Will always be given. There is a table in your book with it. The dielectric constant is a lot like the index of refraction, right? It's just a constant that depends on that material. So whatever it is, you're sticking between capacitors. Capacitance increases by a factor of the dielectric constant. And so if we want to know how, Teflon increases capacitance, all we do is take the dielectric constant of Teflon, times it by the normal capacitance that we have, and that's the new capacitance. I'll show you the formula for that in a second. Same thing for the electric field, only we divide by the dielectric constant to get the net electric field. Right? And so you can see, again, with a dielectric, the capacitance is simply multiplying by the dielectric constant. The net electric field with a dielectric is the normal electric field divided by the dielectric constant. So capacitance goes up and electric field goes down. The electric field goes down for a really cool and interesting reason that I'm going to briefly describe to you and try not to bore you to death. So when I put an insulator in, I know that insulators, they don't exchange electrons readily. That's why they're insulators, right? They don't pass them along to anything else. But they do what we call polarization, which is kind of like what a water molecule does. It has partial charges. And so within this, right, as I run an electric field through it, all of the electrons are kind of attracted to this positive plate, right? And then all of the nuclei or the protons of those atoms are kind of attracted to that negative plate. They kind of flip, right, to be that. The electrons point towards the positive, protons point towards the negative plate because opposite charges attract. And so what this does is creates a partial negative and a partial positive charge in that dielectric. I have the electric field of the parallel plate capacitor still running in that same direction from positive to negative on those plates. This polarization makes its own little electric field though, and it points in the exact opposite direction. So within this there's a little electric field. Didn't say anything about electric fields being in insulators, right? They can be. It points the opposite way. And because the electric field is a vector, when we add this plus this, the net is much smaller than the original. Once I put that dielectric in, I add an opposite vector. And because of vector addition, the overall electric field gets smaller. Right? That's why we are dividing the original electric field by the dielectric constant. Alright, so I've got your homework and tries for this. What we can do, if you guys want to, is simply go through the homework together, right, for this whole chapter. I literally just took half an hour of our lecture, and we've got the rest to do. And so let's work on those homework problems together.